This is Bill Foote at Stats 1, and we are in the realm of the third lecture, binomial ups and downs. We already did part 1, where we papered and penciled our way through to a model. And part 2 is right here, where we built a simple binomial model, the same one, ported it, transport in a sense, but ported it into Excel. What we did last time in part 2, and this is now going to be part 3. In part 2, we built this. We did factorials to do a combination. We did p to the x power, which are the number of successes, the number of waters, and 1 minus p being the hypothesis, being the proportion of lands. And it's still counting the ways, no question about it. And we're multiplying all the way through, because we have 3 different ways to get this result. And we did a grid of that as well, binomial tree. So go back and look at that, refresh yourself. But this time around in part 3, we're going to do 2 expansions. We're first of all going to replace this formula with another formula, the binomial formula. Let me just write it in here immediately. You'll see that everything remains the same. Okay, so this great big long formula is going to be replaced. Goodbye. Notice we're using named ranges throughout, and it helps us understand what the formula is. Factorial of n, factorial of x, factorial of n minus x, p to the x, 1 minus p to the n minus x, where p is held in cell F7. There it goes. Get rid of this. We're going to use the binomial, just putting it on caps so that we can see it a little bit more easily. binom.dist will perform the same calculation, supposedly more efficiently. I don't have a timer on this. And it asks us for a number of things. The number, and then trials, and then the probability. Well, the number is going to be x. Now we have to use lowercase x. The number of trials is the number of observations. That would be n. And the probability is going to be whatever conditions this, it's really the proportion, that hypothesis, which is held in F7. We have one more thing to do. We want to not use a cumulative area under the curve. What we want to use is the probability mass, which is technically the derivative of the area under the curve. Calculus concept, very, very helpful. When we write in false, you can see what's coming up here below. It says false probability mass function. And we're not going to get into the niceties of what a mass function is, but right now that ought to produce a 0, and it does. Let's copy this down and see if anything changes to 15, 40, and 45. Nope, all the same computation. That 38 is 37.5, 42, 2, 14, 1. All of these are the same. So we're going to use the binomial formula. The other thing we're going to do is we're going to expand our 5-point grid into an 11-point grid. And then the thing we're going to do after that is we're going to create using this grid, we're going to create a 3-curve visualization of this final probability, this thing called the posterior probability of hypothesis given the data. And this is our plausibility index. We're going to create the relative numbers relative to what's in this column G, which is the probability of data given a hypothesis, which is calculating this, times the probability of an hypothesis occurring to both and. We're going to add those up, get a sum, and look at the relative size. And the relative size now is a little bit finer because we're using a finer grid. We use 1,000, and this is on the assumption that between any one of these, we can find another continuous. P is continuous. The data is binary. We're mapping binary into continuous. It's an amazing mathematical thing. Okay, so let's, without any further ado, let's get on with this. I am going to copy over some things here into the new spreadsheet that I'm creating for this purpose, which is called binomial 11. The binomial 11. There we go. So I don't have to write this again. And we're going to do something new here. We're actually going to create a grid of P, of the proportion of water. Now, this will only take a couple of minutes, but let's borrow from the other spreadsheet, so I don't have to write it out again. We use this old spreadsheet. I'm going to use those categories. Watch what we're going to do. We're going to create a grid. Oh, somewhere down here. This looks good. Let me do it right here. Okay, max, min. So we're looking at the maximum of the grid. Maximum of the grid is 1.0. The minimum of the grid is 0. It's a very simple grid. And how many intervals? Well, that's a good question. Oh, don't worry about logic supplement. That's coming up in a later one during some requests. But just look at what we're doing. We have a 0, and we're going to 1. We're going to divide it up into, let's say, 5 intervals. Each interval will be max minus the min. How many intervals are there? There's actually only 4 cuts in the board. If this is a board, the 0 is already cut, the 1 is already cut. You actually have 4 cuts, 4 intervals. There's interval 1, 2, 3, 4, 5. Okay. Now, if we want 5 nodes in the grid, okay, 1, 2, 3, 4. So that's 0.25, 0.50, 0.75. Oh, that's 1.0. I can't have 5, right? Okay. That's wrong. You can only have 4 intervals. You've got to take this kind of idea. There we go. And it's incorrect to say 5 nodes is 5 cuts, actually. We're going from 0 up. There's actually, we only have to cut the board 1, 2, 3 cuts for 4 pieces. There's only 4 pieces in this. And the mistake is not understanding that there's a beginning and there's an end to this. Okay, that there's a beginning node, and an end node, and nodes in between. Yes, there will be 5 nodes. Same idea, carrying this to 11 without making that mistake. I will break this up. Start off with 0. We want to end up with 1. And there are 11 nodes. So there's 11 minus 1 intervals. And actually 11 minus 2 cuts if it were a carpentry situation here. This here's node 1, node 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 nodes. Count it off. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 intervals. Going back to the spreadsheet, the number of intervals, we'll just call this intervals, is 10. Now, the width of each interval will be equal to, and let's use our named range capabilities here. Highlight all of those formulas, create, use the left column. There we go. We can see this a little better. Equals max minus min in the numerator divided by intervals in the denominator. I better spell that correctly. 0.1. No kidding. It's 0.1, right? Yeah, but if we have irregular maxes and mins like we will have in the next lecture, we might start with 2, end up with 43. We're going to have some equally spaced, but not as even a split between the two. Let's put this here. Now, what we're going to use this to create our P grid, our grid of proportions right here. Call this H. 1 will be equal to this first one plus 1. That will make 2. Okay. The P grid will start with the min, which is 0. The next node on the grid will be equal to the prior node plus the width of our 10 intervals, 0.1. Now let's just make these numbers. Let's just copy and paste, Control C. That'll be 3, 4, 5, 6, 7, 8, 9, 10, 11. And notice the check on this routine is that it begins with 0 and ends with 1. Now that should be exactly the same as the max. And as a matter of fact, you can always put a data check equals if that number equals the max, type in correct. Give yourself a pat on the back. If not, type in better change this. More pat on the back. And that's an if statement with a condition. And this would, if the condition is true, you write correct. If it's not true, you write better change this. And it's correct. So that's one way to audit your process. Now, the probability of this, there are 11 nodes. Well, we're just going to say it's equal to 1 over interval plus 1. Well, intervals, there are 10 intervals, and plus 1 makes 11 nodes. And it didn't like that. What didn't it like? It didn't like the word interval. It didn't pop up. Where is it over here? Ah, it's intervals, that's why. How many intervals? Okay. Always a problem. Plurals, when you use upper, when you use lowercase. And it's contextual, and I should have read that. There we go. We're going to say these are all equally likely, given an assumption of we just don't know any better. Okay, make these also into numbers. And now the probability of data, given the hypothesis, let's port over the data. And the data is going to look like this. Just going to bring over those cells so I don't have to write them over again. And I'm doing a 9 and a 6 here as an example. So we toss globe 9 times, and 6 out of those 9 times ends up being water. Remember, we're still doing water. X is water here. But we've generalized the model to any binary situation, like acceptance of a proposal, rejection of a proposal would be a good example. And our quest for a little better rendering, otherwise known as a grid. No, that doesn't work. Let me go up here and change that out because I need another row. There, that will work. I'm just going to call this N again. And that X again. Sum is good, okay. And no, I want to call that X. Okay, I'm going to make the numbers that will appear below them formulas, so we can again continue to have in cell documentation of what we're doing. So our original one was 2, wasn't 2, it was actually 3, right? Three. And 2. Well, there were 3 tosses of the globe, that's what N stands for, and 2 successes, waters, that's what X stands for. So far, so good. And the probability, we're going to use the binomial formula here. Dist, and it will be written as X N. The probability will come over from E7 in this case, and false, so that we get what is known as the probability mass function. That's the thing that's lumped up. That's called the probability mass or density function. Depending upon if you're, well, I'm not going to say anything about where that might have come from. Just copy that down. You see some very small numbers down here. That's 0, and that is 0. We will format this to get rid of the scientific notation at the bottom. Make your notation consistent. Sign of detailing. There we go. So we're going to get a grid where 70 is closer, not 75. Notice that. Very interesting. Do our multiplication over here of both the hypothesis occurring and the data being observed given this hypothesis. Let's also at this point to number, and this way the format will also be copied. Remember what's inside each cell. Lots of details, including the value, but also the formats. Okay, we see those are uniformly small numbers. We don't care that they're so small. We're worried about the relative value in the next column. Okay. Actually, I'm going to move this whole thing over. Control X. Put it over here so my columns line up. All right, say yes. There we go. And if I take this data, D is for data, spread it across 2 cells and say merge, does that very nicely. It also spreads the formats. Let me also put boxes around this and this. Now, what is the sum? It's the sum of this product of both the probability of a hypothesis occurring and the probability that we see this data given that very hypothesis. Both and gives that. It's a counting principle again. And the sum equals sum. I like using spaces. Now, if I do a shift control down, it selects all the way down to the last non-empty cell. Nice. Put another parenthesis in there. There we go, 23. Well, there's actually a meaning to that number. It's technically the probability, seemingly, of the hypotheses occurring. Well, kind of. Okay, that's one way of looking at it. Okay, now this will be the relative strength of each of these jointly determined hypothesis being true and this data being true in the presence of the hypothesis. Okay, so we do this just like we did before, divided by this variable, not variable, this cell name called sum. That's of course 0. Make that a number and spread that all the way down to the And now we're watching this. We know it's 70%. It is the highest probability, plausibility of this hypothesis given this data. We can also do what is the probability of the hypothesis being less than P given the data. Well, that's also known as the cumulative probability. So this is a relative. It's relative. It's relative to the whole sum. It shows contribution. And cumulative shows, well, cumulative. It's a cumulative sum. The first one will always be equal to the first relative probability. There we go. And the second one will be equal to the prior relative probability that we have, the prior cumulative, and add the increment, I8. Go down one more. See, it's accumulating. Go down one more. It's accumulating. Spread this down. And we should get 1 at the end. We actually get it before then. And that's fine. So now we have all of these occurring. Let's now do something with it. Let's visualize it. Now, the visualization is going to take place in a number of steps, but the most important step is what we're going to do next. What do we want on this visualization? Let's wireframe it very quickly. That was our nodes. I want to have a graph. Here's the full canvas of the graph. The plot itself, let me just. Up there, so it's out of the way. Yeah. The plot itself is going to be in a plot area like this. We're going to have one plot that looks like this. Oh, that's interesting that happened. There we go. Back the way it should be. And that is the probability of H given D, okay, that relative probability. We also want another plot, and this will be the cumulative. And the cumulative will go up like this. And that will be, I'll just put Q sum of the probability of H given D. For all of you calculus buffs, is the integral. It's a calculation of the area. So each one of those points on that orange curve will be an area. What else do we need? Okay, we are going to need a title. We're going to need an x-axis, which will be the p's, going from 0 to 1. We will need 2 different y-axes. And the reason for that is the minimum and maximum of the Q sum is 0 to 100%. But the minimum and the maximum of the probability of the hypothesis given data also starts at 0, but only goes as high as 18. So they're very different scales, but we want to be able to have a good integrated visualization. So we have what is called a y1 or a primary y and a y2 or secondary y. each with their own title. So we have 3 axis titles and 1 main title. And there's our wireframe. And then we go to our client who's going to consume our analysis, and they nod, yes, this is a good idea. Okay. So let's use that. And let's start building that idea. So we have title here. I will just say water, almost everywhere. Just being snarky. Okay, just to show we can put a title in there. We have the x-axis, which is the horizontal axis, and we're going to use the p-values. I can take this directly from our table over here, which remember is a visual, or I can put words there. We have the y1, the primary y-axis, and that is also going to come directly from the table. Nothing up our sleeves. It'll be that. The y2 axis, and that's also going to come directly from our table. And we'll want to write this as a Q sum. And it will be this more complicated expression, very mathematical of us. So we have the titles. Okay. Now, one more thing I want to point out. Let's go back to the wireframe. There is a third thing I want to put on this graph, and that is this. The most plausible, which is going to be called the maximum. The maximum posterior probability. And this is also the most plausible. Comes under a lot of other names, but you can see it's the maximum height. And therefore, this particular proportion on this grid becomes our primary candidate. But let us not ever forget, and remember lecture 0, we are looking at all of the information on this blue, because that's what we're really after. We want to know the plausibilities up and down the line, from a low proportion of water to a high proportion of water. But it's most likely, and likely is not a bad way of putting it, it's most plausible, but the most plausible answer, the most plausible conjecture or hypothesis is the one most consistent with the data that happens at, in our particular case, 0.70. We want to put a vertical line there. Now, let's go to this setup, which is in chapter 4 of Foot's online book. And so we have the y1 axis, we got everything here. Let's copy these down. And bring them over. There we go. Now we're going to have the max, the optimal, And we're going to set up what is called an AB line for that vertical. Let's put these under the format. Now, the max is the max of something. Something. Finish this up. See things a little bit better. What we want is the max of column I. See, it's 18, and it's going to refer to the left to hypothesis 8, row 8 of the hypotheses. And if you knew what was in row 8 in column E, you would say, oh, it's 0.7, right? Okay, so row 8 is also where 18% occurs. Okay, so we're going to use that and use two functions in Excel to help us here. So the max will be the max of this whole row, of this whole column here. Let's indicate that. So the max is that. And we want to find, if it's 18, we want to find 0.7. Now, it's not going to be 0.7 every single time. It might have different data and it'll have a different row number. So what is the row number? Let me use a formula called match. Match this 0.18. Okay. Where the 18 actually occurs, it's in this column. So match P29 in column I, 7 to 17. Want an exact match, put in a 0. Press, do the right parentheses and then press. And you see it's in row 8. Okay, we know it's in row 8. That's also hypothesis number 8. That's a good index. That's why I put the index in there. It helps point to that. But that's not our answer. Our answer is 0.7. So we use this match inside of another function called index. So index our hypothesis column. There we go. All of these 11 hypotheses. Index this, and this is a row column situation. So okay, in that column at row 8, comma, and we put a space there because we need to put a column there, but there is no column, just a right parentheses ought to do it. It comes up 0.7. So index and match is a lookup function. And it runs off of the grid that are cells, but a very specific grid, the grid defined by our columns of probability of H given D and P. Okay? And it allows us to match whatever is in column I with whatever is in column E. And it does so perfectly. So index and match, you can look this up in Wayne Winston. It is one of the most useful set of functions in all of Excel for data wrangling. know it well. It's great to put it on the resume. Most interviewers won't even know what it is, and you can say, well, this is what it is. Okay. Now, this is just the title of what will be the vertical line, and the vertical line will let's just do the vertical line again in a wire context. So the vertical line here, first of all, we're using the y1. The vertical line, its coordinates start at 0.7 in our case. And this first point is 0 units on the y1 axis. So coordinate geometry. The first one is the x, second one is the y. So what is this next one? Well, it's also 0.7. You got to go 0.7 down, but how many up? Well, we already found it is 0.018. It has a different x and a different y. It's called the AB line because this is point A and point B, so we affectionately call it the AB line. In many computer implementations of graphics, vertical line. We also do horizontal lines the same way. So remember what x is. It's always going to be 0.7, but one of the points is going to be 0 and the other is 0.18. Let's put that into Excel and run an AB line. So here's point A, here's point B, and let's give them a little visual assist. So for X, it's going to be the max, the optimal, 0.7, and Y is going to be 0. For B, it's also going to be the max, but its height is going to be this 0.8. And there we go. Now, the thing is, the x's will be equal and the y's will be here. We're going to need to put this into the graph row-wise. You'll see why in a moment. There we go. Row-wise. I'm going to do it this way just to help us along. Let's put these up here like this. And after all of this work, we are almost ready to build a plot. Actually, we've been building the plot all along using all of these parameters. So this is the setup. We have set up the grid, we have set up the plots. Let's start filling this in. Now, my preference isn't to use bar plots, it's to use line plots. But the way I think about these plots, especially in Excel, a lot easier to think about it this way, is, well, first of all, we're going to insert. What are we going to insert? A bunch of charts. There's only one chart I tend to use a lot, and that's a scatter plot. And let's make them nice and smooth here. Scatter plot with, now there's our blank canvas, the scatter plot with down here. So we can see what we're doing. I think we'll be able to get most of it in here. Okay, that's pretty good. we have titles. We got all sorts of stuff going on here. Let's not worry about the titles. Let's put in this. Now, we have chart design and format that appear when you select the chart here. They call them charts. Doesn't matter. And we want to do select data. I never put anything in up here. It's for a different purpose, a different day. But I do want to add something. And the series name is helpful for documentation. The first series I want to put in is this series, and that'll be the series name. That's what's going to come up on a legend, by the way. So we could also call the series whatever we want to put down here on the Y1 axis. So I can choose that instead. Okay, why don't we do that? And the X values are all going to be, it automatically thinks we want a title, by the way. That's not going to be the title we'll use. The X-axis is going to be all of these P values. Okay. In the Y-axis, it automatically puts in a primary Y-axis and 1. You can see that's 1. You want to get rid of that idea and put equals, and the Y-axis are going to be these values. Create our coordinates that way. You can see it's already beginning to form. Isn't that lovely? And we'll fix that in a moment because we don't have anything that goes up to 120%. So 1.20 will have to go. But let's not worry about that now. Let's add one more. And this will be the Y2 situation. Just a cumulative sum. And again, we choose the X-axis as 0 to 1 over here. Get rid of this nominal value. Look at what happened already. Our chart, our curve has already been depressed. We need to fix that. Equals for the Y. So say OK. Now, it's an S shape. It's called an ogive. Don't worry about that. And right now, that's not going to work for us because these are incomparable. They're correct, but they're incomparable. But before we do anything else, we say OK. But not yet. We have one more to put in. I don't want to put that there. One more to put in. What calls move? You're dead. Not quite. I want to put in this max. The maximum a priori, the MAP technically is what it's called. That's a title that we're going to use for the AB line. And here are the X values for the AB right here. Remember this row is 2 X values. We're creating a line, 2 X values and 2 corresponding Y values. Done. Okay. Look at that. Made a line. How clever. Now you can say, OK, please do so. Now it's saved. We have a bunch of things we need to do here. The very first thing I want to do is get rid of this 1.0. So put your cursor on any number on the X-axis and say format axis. And this format dialog comes up. Notice this 1.2 for the maximum. Take that 0 and get out of there. Press enter. There we go. Okay. We're not going to do anything with the other axes yet because there's one more thing I want to do. Let me get rid of my face here and get rid of this. Okay. Put your cursor on this. Well, no, notice what's happened. They're both measured on the same y-axis. We want to split that out. We had the idea that we need 2 different axes. So right-click all of those and format data series. Notice the first thing that comes up is a choice between use this primary or Y1 axis versus a secondary. Let's choose the secondary. Oh, it's beautiful. It's exactly what we wanted. And that goes from 0 to 120. We want to get rid of that idea. That 1.6, because 120 doesn't exist. Can't exist in probability. Everything has to add up to 1. Okay. And the other one goes up to 0.2. That's okay. It's a possibility. Okay. And all of these will shrink and so on. But the 0 to 1 will always be 0 to 1. We have almost everything we need here. Let's just see the chart area. Select that. And on the right comes up a bunch of pluses. Chart elements. And for whatever reason, there we go. On the left, we have axes. The axes titles, automatically they're put in there. And chart title. We also want to put in a legend, and we want to preserve real estate, as we say usually. Put this at the bottom. You see, we automatically pick up the labels down here. They're already dynamic. Now we want to have a dynamic chart label. And the way we do it is we highlight the text of the chart title, go to the formula line, equals, and choose water, water everywhere. We'll change that, of course. Axis title, highlight the text by pressing on one of the characters. This is critical. Go to the formula line, equals, and this is the Y1 axis. Press enter. Comes right in. You can change that too. The Y2. Press on, select, go to, equals, Y2 axis. Done. Axis title. For the X-axis, press and select, go to, equals, and for some reason or other, oh, there it is. I thought I'd lost it. It's just P. We put whatever we want into there. So we have a complete graph. There's not much else we want to do here except maybe change this almost everywhere. And what I put in here is double quotes. How much water? And here we could do an ampersand and put in some coordinates. Ampersand, open parentheses, space, n equals another close quotes that gets that phrase in there with the spaces, ampersand. And now we can pick up data like that data. And notice it doesn't look like much. I got to put an equals in front to make it a formula. Okay, it did not like. There we go. It did it perfectly. How much water? N equals, and then I can complete the formula. And automatically changes it. Why don't we also complete more of this formula? Ampersand, text, put a comma there, space, text space equals space, close parentheses, ampersand, and put 2. That's dynamic. And it's so dynamic that if I toss the globe 9 times, and 6 of those times we find water, and this will be the result, still at 0.7. We can label that as well. You can also put the max up there. And if we do that, then we give a complete story, just like this. I'm going to end with this. I like telling complete stories. Oh, double quotes. I'm going to use a colon. B star, okay, I'm sorry, we're using math here, equals, this is the optimal, close that piece of text, ampersand, and choose this optimal one right here, the 0.7. Now we have a complete story. Okay, we can put in whatever data we want, come up with our ever, do this 15 times, and oh, there we go. And there's still only 6. Look at how it changes. If it's 4 and 4, notice what happens. 4 times, look at that, that's great. And 4 times there, but what if we tossed it 8 times? It's perfectly symmetric. We can play with this. Perfectly symmetric p equals 0.5, right in the middle. Okay. We can do a number of other things, but this is enough, and we're going to be using this technique throughout the rest of the course. And I'll leave you with that. And thank you very much once again for your very kind attention.